In this lesson, we'll explore using Riemann sums to find area. To start, let's look at a general setup. Suppose that we have some function here, y equals f of x, and we're interested in finding the area between the graph of this curve and the x-axis, say on the interval 1 to 4, so this blue shaded area. In general, you'll have an interval a to b. So your first step is going to be to divide your interval AB up into n subintervals. So I want to start by finding the width, which I'm going to call delta x, of each subinterval. So notice that the entire length here from 1 to 4 would be 4 minus 1 or 3, or in general would be b minus a. So then the width of each one, if I did 3 subintervals, each one would have width 3 over 3 is 1. If I did 6 subintervals, then they would all have 3 over 6 is 2. If I did 12 subintervals, 3 over 12 is 4, etc. So in general, if you have n subintervals on the interval a to b, the width of each one is going to be b minus a over n. So we're going to start just by dividing our interval up into subpieces so that we can use our rectangular approximations to approximate this area using rectangles. So we'll start just by dividing it up into pieces. And now I'm going to find the right, you could also do the left or the midpoint. For here, we'll just do the right endpoint of each subinterval. So here, I'll make this a k since we used k's before. So I want to call x sub k the right endpoint of the kth subinterval. So for example, x1 would be the right endpoint of that first subinterval. So to get to that point, I would start at my number a. Remember, in general, I want to be on the interval a to b. In this case, that would be 1. So in general, it'll be a plus delta x. If I wanted the right endpoint of the second interval, now I'm starting at a, or in this case 1, and going over 2 delta x's. So to get the kth subinterval, I always start at my endpoint a, and I go over k delta x's. So the right endpoint of each of these is just a plus k times delta x. And remember, I'm doing this because I want to be able to find the area of these rectangles. So I know that my area is base times height. The base of each of these rectangles is delta x, just the base or the width of each subinterval. And then the height is just the function value at that right endpoint. Again, you could do left or you could do midpoint. We'll do right endpoints here. So the height is just that function value. So the area of each of these is just delta x times the function value. And remember, we have values for these things. So delta x we know is b minus a over n, and f of xk, we found xk, that's the right endpoint of the kth subinterval, so that's f of a plus k times delta x. So, and again, we know what delta x was. It was b minus a over n. So this is just f of a plus k times b minus a over n. And again, this gives us the area of one of these rectangles because it's just the base of the rectangle times the height. So then if I want to get the area under the curve, I just add up the areas of all the rectangles. So I get the height times the base, etc. The area of each of these rectangles is the height times the base, and then I just add them up. And finally, I can write this now in sigma notation. So this is the sum from k equals 1 to n of, again, the height of the kth rectangle. So this should be f of x sub k. So remember, again, x sub k was that right endpoint, so it's the function value there, times delta x, which is the width of each rectangle. So finally then, if I want it to get the exact value of the area, I need to take the limit as the number of rectangles goes to infinity. So as we've seen, if we just do an approximation, then we'll get error in our area estimation. But if we let the number of rectangles go to infinity, then the area, adding up the areas of all the rectangles, will give us the exact value of the area under the curve. So let's do this in the context of a particular example. Again, let's just summarize the procedure. We find the width of each subinterval. We then get the right endpoint of the kth subinterval. We then draw the rectangle with height f of x sub k. That gives us the area of each rectangle. We can then add up the areas of each of those rectangles. We can use our sigma notation to express that. And finally, we'll take the limit. Again, this is in x sub k here. We'll take the limit as the number of rectangles goes to infinity. So this expression here is your f of x sub k, the height of the kth rectangle. Okay, so let's look at this again in the context of a problem. Again, though, the thing to remember is that all we're doing is adding up areas of rectangles. So it's height times base plus height times base plus height times base, and we're doing that for n rectangles, and then we're letting the number of rectangles go to infinity. Okay, so let's take a look at the graph of y equals x squared on the interval 0 to 4. So the first thing I want to do here is divide this interval into n equal subintervals. So here I want to go from 0 to 4. So I want the area under this graph from 0 to 4. So the width of each one we know is b minus a over n, which in this case is 4 minus 0 over n, or 4 over n. Then what I'm going to do is let x sub k, once I have one of these intervals, I'm going to let x sub k denote the right endpoint of the kth subinterval. So I'm going to start at 0, and I'm going to go over delta x k times to get to the right endpoint of the kth subinterval. So I start at 0, and I go over delta x, which we knew was 4 over n, k times. So I just get 4 times k over n for my x sub k. So this gives me 4k over n. So then the next thing I'm going to do is say, okay, I'll take my subintervals. I know that the right endpoint here is 4k over n. This is the graph of y equals x squared. So then the height of this rectangle, so my x value here is 4k over n. My y value is just 4k over n all squared. So my height is 4k over n all squared. I can then get the area of one of these rectangles. So the area of one of the rectangles is just the height, so f of x sub k times delta x. Again, if I think about taking a rectangle and I use the right endpoint, so delta x is the base, f of x sub k is the height. And now for this problem, I actually know those values. So I know that f of x sub k, we found that height to be 4k over n quantity squared, and our delta x was 4 over n. So now I have my expression for the area, and now we can just take the limit as the number of rectangles goes to infinity. So I can plug in, we have that our height was 4k over n quantity squared. Our delta x was 4 over n, and we want to take the limit as n goes to infinity. So this gives us, multiplying out 4k over n quantity squared, that gives us 16k squared over n squared, and then we multiply that by 4 over n, so we get 64k squared over n cubed. Now remember from our summation formulas, 64 over n cubed, that doesn't have any k's in it, so that's just a constant that can come out front, and then we get sum k equals 1 to n of k squared. And that's one of the formulas, the sum of the first n squares, that I'll give you. So that's n times n plus 1 times 2n plus 1 over 6. And now we just have a limit as n goes to infinity. And we've had a lot of practice in class doing those. So this just becomes limit n goes to infinity, 64 over n cubed. I'll expand out the top. 64 over 6 gives us 32 over 3, and then this final limit, 2n cubed plus 3n squared plus n all over n cubed, that becomes 2 plus 3 over n plus 1 over n squared, and as n goes to infinity, 3 over n and 1 over n squared go to 0, so that just gives us 2. So we end up with 32 over 3 times 2, or 64 over 3. So again here, the idea is that we just added up the areas of our rectangles, so we have our height times our width, and then we take the limit as the number of rectangles goes to infinity. We had to find the height of each one and the width of each one, and then we just simplified that expression, pulled out our constants, used our summation formula that I'll give you, and then we just computed the limit. So to conclude, the area between the graph of y equals x squared and the x-axis on the interval 0 to 4 is equal to 64 over 3.